On September 23, 1999, NASA's Mars Climate Orbiter approached Mars after a 9.5-month journey across 416 million miles of space. The spacecraft had launched correctly. The navigation team had been tracking it the entire way. The trajectory looked right. The systems were functioning. Then, as the orbiter fired its engines to enter Mars orbit, it disappeared. It had flown too close to the planet. Instead of entering orbit, it skimmed the upper atmosphere at the wrong angle and broke apart. The mission was over. $327.6 million in total program cost. 9.5 months of flight, gone in minutes. The subsequent investigation found the cause within days. One software module, built by a contractor, was outputting thruster force data in imperial units, pound force seconds. The navigation software receiving that data was expecting metric units, Newton seconds. 1 pound force second is approximately 4.45 Newton seconds. Over the course of the 9-month journey, every small thruster correction had been calculated using the wrong scale. The errors accumulated, the trajectory drifted, and by the time the orbiter reached Mars, it was 170 kilometers off course, the direct result of a unit mismatch that had been present in the system since before launch. Two systems, one interface between them. No agreement on what the numbers meant. The numbers were transmitted correctly, they were received correctly, they were stored correctly, they were used incorrectly, because the unit they represented was never specified, never checked, and never enforced. A number without a unit is not a measurement, it is a quantity waiting to be misunderstood. Most people encounter the units problem long before they work with spacecraft navigation. You open a file from a colleague and the distances are in miles. Your system expects kilometers. The calculation runs, no error appears. The result is wrong by a factor of 1.6. You receive a temperature reading from a sensor. Is it Celsius or Fahrenheit? The column is called temperature. The value is 98. Is the server room critically hot, or at a perfectly normal human body temperature? You don't know. The column doesn't say. You import a dataset of product weights. Some rows came from a supplier in the United States using pounds. Some came from a supplier in Germany using kilograms. The column is called weight. It contains numbers. It contains nothing else. Your system treats them as the same unit. The shipping calculations are wrong for half your catalogue. No error is thrown. The wrong numbers look exactly like right numbers. In each case, the problem is identical to the one that destroyed the Mars Climate Orbiter. A number was passed between two systems. The unit that gave the number meaning was not transmitted with it. One side assumed one thing, the other side assumed one thing different. The assumption gap became a calculation error. The calculation error became a consequence. The consequences are rarely $327.6 million. But they are real, they are common, and they are almost always invisible until something downstream reveals them. Let's go deeper into why this happens so persistently. When a system is first built, the unit is usually obvious to everyone involved. This system is for a US company. Distances are in miles, weights are in pounds, temperatures are in Fahrenheit. Nobody writes this down because nobody thinks it needs to be written down. It's obvious. Obvious to the team that built it. In the moment they built it, with the context they had at the time. Then the system grows. A new engineer joins, who spent 5 years working in Europe. A new data source is integrated from an international supplier. A new feature requires importing data from a third-party API that doesn't document its units clearly. A new market is entered, and a localization engineer adds metric support for the new region without updating the original columns. None of these changes announce themselves as a units problem. They look like normal growth, but each one is a new assumption entering the system. An assumption that may or may not match the assumption already baked silently into every column that was built before it. And the original assumption is still there, undocumented, invisible, holding up every calculation that depends on it, waiting for the first moment a new assumption contradicts it. Here is something that makes the units problem distinctively hard to detect. A type error is caught immediately. You try to store text in an integer column. The database refuses. You fix it. A null error is often caught quickly. A calculation returns null. The report shows a blank. You investigate. A units error produces a valid number. The type is correct. The value is in range. No constraint is violated. Everything the database can check has been checked. The number is stored successfully. It is precisely, accurately, verifiably wrong. There is no such thing as a database constraint for units. You cannot write a rule that says this column must contain meters, not feet. The database stores a floating point number. It has no concept of what that number represents in physical reality. The enforcement has to happen at the boundary, at the point where data moves from one system to another, from one team to another, from one context to another. And boundaries are exactly where documentation is thinnest. Assumptions are most likely to diverge, and the people who know the context are least likely to be the same people on both sides. This is why the Mars Climate Orbiter failed at the interface between two software modules built by two different teams, not inside either module, at the boundary, where the number crossed from one context into another and took its unit with it only in someone's head. Let's look at another real failure, closer to everyday data work. In 2015, a major European hospital network implemented a new electronic health record system that integrated data from multiple existing systems across different countries. One of the integrated systems was a legacy database from a hospital in the United Kingdom that stored patient weights in stones and pounds, the traditional British measurement system. The new integrated system stored weights in kilograms. The migration script converted the values, or it attempted to. The script correctly identified weight values from the UK system and converted them into the target column. But the conversion was applied inconsistently. Some records were converted, some were not, depending on which migration batch they fell into and which version of the script processed them. The resulting system had a mix of values in the weight column. Some were in kilograms, some were in stones, expressed as a decimal number. A patient weighing 11 stones, which is approximately 70 kilograms, had records in both units depending on which batch had processed their data. The column said weight, the values said different things. The inconsistency was discovered when a pharmacist noticed that a drug dosage calculation for a patient produced a result that seemed far too high. The calculation was based on the patient's recorded weight. The weight in the system was the unconverted stones value, interpreted as kilograms. The patient appeared to weigh nearly 70 kilograms. They actually weighed 70 kilograms. But some of their records showed a weight of 11 stones, interpreted as 11 kilograms, far below their actual weight. The dosage system had used the wrong record. The hospital caught it before administration. The audit that followed found hundreds of records with inconsistent weight values across the same patient's history. The database had done everything correctly. It had stored the numbers it was given. It had no way of knowing that some of those numbers were stones and some were kilograms, because nobody had told it. A column called weight, containing a floating point number, is equally happy, storing 70 kilograms or 11 stones. It cannot tell the difference. It was never designed to. Now let's talk about what the Mars Climate Orbiter investigation actually recommended, because it's directly applicable to how you design data systems. The review board's primary recommendation was deceptively simple. Every interface between software components should explicitly specify the units of every value being transmitted, not in documentation that lives separately from the code, in the interface itself. In data terms, this translates to, the unit is part of the data, not part of the context. A column called weight kg cannot be misread as pounds. A column called distance miles cannot be confused with kilometers. A column called temperature Celsius cannot be mistaken for Fahrenheit. A column called duration seconds cannot be misinterpreted as milliseconds, a unit's mistake that has caused more system failures in software than almost any other single source of error, because seconds and milliseconds look like the same kind of number and differ by a factor of exactly 1,000. The unit belongs in the name, not in a comment, not in a rebie, not in the shared understanding of the team. In the name, where it cannot be separated from the value it qualifies, where it is visible to every developer who queries the column, where it is present at the exact moment the assumption is being made. The second lesson from the Orbiter investigation is about interface validation. The thruster module and the navigation module had been tested extensively in isolation. Each module was correct on its own terms. The failure was at the boundary between them, and that boundary had never been tested end to end with a check that the units were consistent. In data system terms, Integration tests must verify units, not just values. When two systems exchange data, the test suite should include a check that the units on one side match the units expected on the other. Not just that a number arrives, that the number means the same thing on both sides. The third lesson is about what happens when unit conventions change. A system that stored distances in miles for 5 years is asked to support a new international market. The team adds metric support. They create new columns in metric units for the new market. The old columns remain in imperial for the existing market. Now the system has 2 columns representing the same concept in different units. Any query that joins or compares them will be comparing miles with kilometers, with no automatic conversion, no error, and no indication that anything is wrong. The solution isn't to have 2 columns. It is to store a canonical unit internally, always kilometers, always kilograms, always seconds, and convert to the user's preferred unit at the point of display. One internal representation, one set of calculations, no ambiguity. The unit is fixed inside the system. The presentation varies at the surface. This is the same principle that governs time zone handling: store in UTC, convert for display. The canonical representation eliminates the ambiguity. The conversion is the last step, not an invisible assumption somewhere in the middle. Units sit at the intersection of 2 things. Databases are not designed to handle physical meaning and human convention. A database knows that a column contains a floating point number between 0 and 1000. It does not know that the number represents a mass. It does not know which mass unit was used to express it. It does not know that 70 in one context means kilograms and 70 in another context means a patient who has been dangerously misweighed. That knowledge lives outside the database, in documentation, in column names, in team conventions, in the shared understanding of everyone who has ever touched the system. Shared understanding is the most fragile thing in any organization. It dissolves when people leave. It fractures when teams grow and diverge. It evaporates when systems are integrated across organizational boundaries. The Mars Climate Orbiter didn't fail because engineers were careless. It failed because shared understanding, the assumption that pound force seconds and Newton seconds were the same thing, was never made explicit at the one place where it mattered, the boundary where the number crossed from one context into another. Every number in your database is a measurement of something. That something has a unit, and if the unit isn't written next to the number, it exists only in someone's head. When that person leaves, or when the system grows, or when 2 teams integrate their data for the first time, the unit disappears. And a number without a unit is just a quantity waiting to be misunderstood. The Mars Climate Orbiter was one of 2 spacecraft launched as part of the Mars Surveyor 98 program. The second spacecraft, the Mars Polar Lander, arrived at Mars 3 months later in December 1999. It also failed. Contact was lost during entry and descent. The cause was determined to be a software error in the landing leg sensor system. 2 spacecraft, 2 failures, same program, same year. The total loss to the program was approximately $655 million. The Mars Climate Orbiter failure alone, at $327.6 million, remains one of the most expensive software errors in history and one of the most precisely documented because the cause was so unambiguous, so preventable, and so ordinary. It was not a failure of engineering. It was a failure of communication between 2 systems that spoke the same language but used different units and never checked whether they agreed.